With the melting points and boiling points, just for reference, okay, as a reminder, what you are responsible for is 2, 3, 4. Okay? In this class, you're responsible for being able to tell the difference between 2, 3, and 4. Number 1 is in a more advanced topic. That would be something that you would see maybe in 151, but definitely in organic chemistry. Wow, there's a massive lag time on my screen. This doesn't bode well for the recording. When we go through and look at vapor pressure, how do we go through and apply this? Well, what was the vapor pressure? Come on, somebody can come up with the obvious answer. It's the pressure that comes from the vapor. Right, well, what is the vapor? The gas. Well, if it's just a gas, why don't I just say gas pressure or just say pressure? Okay. What this is referencing is the pressure from a liquid and not the pressure from the liquid pushing on the container. Pressure is only measured from a gas. Okay, well, if I have a liquid, why am I referencing a pressure then? What do liquids naturally do? They evaporate and turn into the gas. The more the liquid evaporates, the more pressure we're going to see. Okay? The ability for an individual substance to move into the gas phase on its own without adding a whole bunch of energy is our vapor pressure. Okay? As we change the temperature, our vapor pressure will also change. But typically when we think about vapor pressure, we're concerned about room temperature. Okay? So if I took a look at the vapor pressure of this desk versus the vapor pressure of the water, which one do you think has a higher vapor pressure? The water. Why? I don't accept that. Because our pressure is still the gas phase.
Solids don't put off vapor.
Solids don't put off gases. Most solids do not transition to the gas phase very easily at room temperature. That's why when we have a solid and we put it on the counter, what do we expect to see? A solid. It doesn't change. If I come back 2 days later, the desk is still there. The only reason it's not there is because somebody went through and moved it. If I looked at the water and poured the water on the desk, what would happen in the next day? It would be gone. Not because somebody moved it or cleaned it up, theoretically. It evaporated. It changed phases into the gas state. Right? Why could it do that? It has a higher vapor pressure. Solids tend to have very low vapor pressures. Liquids have very high vapor pressures. Depending on the liquid, you can have higher and lower vapor pressures, and we'll look at another example before we look at the question here.
Is there an exception for solids?
Are there, and so remember, in our phrasing here, I think I've been phrasing it, most solids.
Yeah, that's what I'm asking.
Okay. There are some solids that do transition directly to the gas. Really?
Ooh, yeah. Like
Dry ice. Okay. Dry ice is a block of solid CO2. And what happens when you leave the block of solid CO2 out? It vaporizes. It goes directly into the gas state. So if I look at the vapor pressure for solid CO2, it is very, very high. Okay? Because it immediately transitions into the gas phase. So depending on largely the intermolecular forces present in each of those compounds, those are going to dictate the pressure that we have. So the vapor pressure allows us to get an idea, or can be estimated by looking at the forces present in that compound. Okay? It is a bit more complex than just looking at the forces, because our forces are ultimately a representation of temperature, okay? Energy put in. And if we think about gases, temperature is important when we look at pressure. But is that the only thing that's important? No. What else is important? Gases. The size of the container, the volume of the container, temperature, the moles, the pressure. We have ideal gas law. All of those things contribute to the overall shifting between our gas and our other phase, be it a solid or a liquid. Okay? So when we think about phase transitions, temperature happens to be the most common one. Pressure is also insanely important. Okay? It becomes less important for solids and liquids because what happens when you squeeze a solid?
Stay the same.
It doesn't change. That's because solids don't have any space between the individual molecules. So when you squeeze them, what happens?
Solid.
Well, nothing. They can't move. But if I squeeze a gas, there's lots of space. I can see a pressure change. Okay, so pressure becomes very important for gases and a little bit less important, but still important for liquids, and then virtually not important at all for solids. Okay? Within the realm of pressures that we're used to dealing with, ballpark atmospheric. Okay? Because if we put more pressure behind a solid, do we get different changes? We could push on the wall, well, it didn't change. But what if I put a lot of pressure behind it? I could probably break the solid. Okay. Well, I probably couldn't. Maybe London could. Okay. If we pushed on maybe one of the other walls, not a whiteboard. Okay. So the pressure does have an effect on all phases. It just becomes within our normal realm of pressures, right around atmospheric. Okay. We don't see a large effect with our solids.
So what happens with the dry ice, like when it vaporizes, what happens when you collect that vapor? Like what phase does it go into?
It would just be a gas. So we could collect it as a gas.
Make it another,
Could I get it back to a solid?
yeah.
Yeah. What would I have to do to get it back to a solid? I could drop the temperature. Okay. So I could take that gas and cool it down a whole lot, and that would get me the solid back.
Get it to a liquid?
Can you get liquid CO2?
Yes.
Yeah. Yeah, you can. You have to have a container that will deal with the pressure. Okay. You have to be careful with that. I've seen it is pretty cool. Okay.
I'm excited to learn London dispersion.
I wonder why. Okay. So let's go through and take a look at the question now. Okay, so we have an idea of what vapor pressure is. Okay, we're looking at the pressure that a liquid would give off to form a gas. Okay, based only on the intermolecular attraction, and we really have to say that because we're saying we're ignoring pressure. Okay. Predict which of the following liquids would have the highest vapor pressure. Wow, that's believe it or not, quite a bit. So if we go through and look at this, we want a high vapor pressure. Which means we have what? We have lots of pressure. How do we get lots of pressure? And this is VP for vapor pressure.
By condensing making the container smaller.
Changing the volume is going to change our pressure. We aren't changing the pressure here. This is monitoring the vapor pressure. We're not changing the pressure. We're monitoring the vapor pressure of our substance. If I have a high vapor pressure, what does that mean?
A lot of heat.
You're changing a variable. Don't change the variables.
There's a lot of pressure exerted.
What's exerting the pressure?
It's a force.
A force. The gas. So if we have a high vapor pressure, what does that mean? Lots of gas. Okay, the more gas we have, the more pressure we would see. Okay, so what we're looking for a high vapor pressure is lots of gas. Well, how would I get lots of gas? Eat lots of beans. Beat you to it. How do I get lots of gas?
You gotta have lots of liquid or something to make a gas. You know?
Why would it be in the gas state? Why is oxygen a gas but water not?
Pressure.
So again, you're looking at the pressure, and remember, what's the only thing we're allowed to look at?
Liquid.
The intermolecular attraction. Sorry, I wasn't quite tall enough. Intermolecular attraction. Okay, well, what would dictate if I had lots of gas versus, say, a liquid or a solid? So we could look at the types of bonds, but I want to know what to apply that to. which one would I expect to be more of a gas? A boiling point at 100 degrees Celsius or a boiling point at 20 degrees Celsius?
100 degrees Celsius.
So, boiling point, that's when we transition from the liquid to the gas. At 20 degrees Celsius, maybe we should use Fahrenheit, 20 degrees Celsius is room temperature. At room temperature, it boils and turns into a gas. Or 100 degrees Celsius, it boils and turns into a gas. Which one do I expect to see in the gas state first? The first one, at 20 degrees Celsius. Why would I expect to see that one as a gas? How often are you walking around and like, oh, it's 100 degrees Celsius right now? And I know we live in Arizona, and you're like, but it's 100 degrees during the summer. It's 100 degrees Fahrenheit.
What's 100 degrees Celsius though?
100 degrees Celsius in Fahrenheit is 212 degrees Fahrenheit. We would be boiling, so we aren't at 100 degrees Celsius.
I wasn't technically wrong.
Okay. So if we try and go through and compare those two substances, the lower the boiling point, the more gas we have. So lots of gas means low boiling point. Yeah? Okay. How do I know I have a low boiling point? Touche. Go forwards, not backwards. How do I know I have a low boiling point? What dictates my melting points and boiling points?
You have no gas.
The types of forces. So if I have a low boiling point, that means I have to add a very small amount of energy and those molecules rip apart from each other. Which of my forces is going to use the smallest amount of energy? London.
Ionic. Covalent.
London
dispersion.
dispersion forces. We would want the weakest force. The weaker...
Where were we?
This is why you should have showed up to class earlier, then you wouldn't have been so happy to find out about London. Our London dispersion force is the weakest attractive force.
Hydrogen bond.
No, and biology messes with you. We can address that too, because I'm not happy about that either. Right? So a low boiling point means we're looking for London dispersion forces. We want a weak force. So actually, let's write that. We'd say weak force. And now everybody's going to go through and make fun of you, London. I'm sorry.
My name's really James, guys.
We want the weakest force possible. So we'd look for something that's London dispersion forces. If we didn't find London dispersion, what would we move to? The next one, dipole-dipole force. Okay, so it's always about the weakest force. Well, how do I know I have a weak force? I'd have to know the bonds that are present. So a weak force is going to come from, okay, technically our strongest bonds. Oh, here we go. I got a spin for you. We're looking for the strongest bond. Okay. That strongest bond we would expect to be our nonpolar covalent. Okay. Because it's a strong bond, because it is internally very strong, it doesn't need to interact with other things to prove that strength.
I never do.
See? It works.
I just walk in the gym and I know.
Okay? So we just zigzagged all the way through this to get to, I want to find the strongest bonds. So I now have the information. So really what this question is asking is which of those compounds has the strongest bond? Well, why didn't they ask that to begin with? Because you need to prove that you understand how each of those concepts are interlinked to each other. Okay? So it is a deep question with multiple layers that becomes challenging because you have to know what each of those things mean. Okay? So I'm looking for the strongest bond. So what I would need to do is go back up top and go through and evaluate the bonds that are present in each of those structures. Notice the structures are written as formulas, okay? Just like we did with the melting point and boiling point question. Everybody didn't like that. And we drew out some of the Lewis structures. So you could go through and draw Lewis structures for these to do that prediction. Okay? That is up to you to decide that if you want to do that or not. You're responsible for being able to interpret these as is. So when we go through and look at this,
There's another other way to do it? Like
what I just circle,
CH3.
CH3. So I have carbons and hydrogens. What kind of bond is carbon and hydrogen? This would be our covalent. I want to add the end for this, so nonpolar covalent. As I continue to move through the structure, what do I have there? Carbon to oxygen, which is polar covalent, and OH, polar covalent. Okay. So if you have trouble recognizing that, you should go back and watch the videos from Tuesday, because Tuesday we go through and look at those forces, okay, and evaluate those. And if you go back even to last Thursday, I think we also went through and looked at those forces and identified those relationships. You need to be able to identify those to answer this question. Okay. What about the next one? Nonpolar covalent, nonpolar covalent. Everything here is nonpolar covalent. How about the next one? Those are all nonpolar covalent. That's nonpolar covalent. So this, how would I tell the difference between B and C then?
The oxygen.
You have to read very carefully what's sitting in the middle of that.
A big old bad O.
And oxygen. That oxygen is bonded, frick nuts. That oxygen is connected to carbon, making what kind of bond?
Polar covalent.
Polar covalent. D, what do I have in D? Oh, a bunch more, nonpolar covalent. Well, how would I tell the difference?
The chlorine.
I have to recognize the presence of the chlorine. What's that chlorine connected to? It's connected to that carbon. That's why that circle is really big, so I'm trying to include the carbon in it, which would be a polar covalent bond. Last one. Nonpolar, nonpolar, nonpolar. I also have the S in there, bonded to the C, and that is, don't say ionic.
I wasn't going to say, I was going to say covalent.
Try again.
With a polar.
With the polar, yeah. Polar covalent. All right, so what we've gone through and done is addressed all of the bond types within that. That should already set us up now with the answer. I could have ignored all of that work where we talked through everything. Why does that set us up with the answer? Well, been seeing Sesame Street. Which one of these things is not like the other? Which one of these things does not belong?
Is it A or B?
Yes. It is one of those two answers. Which of those answers stands out as different from all the others?
They're both different. One answer has the extra PC and
B. Okay. B stands out as the different one because it's only nonpolar. If we go through all of the reasoning or zigzagging back and forth, what did we want to find? Our strongest bond. So we want to find a structure that only had strong bonds. That was nonpolar covalent. Which of our answers only has nonpolar covalent bonds? B. So the force generated, and this is why I did the polar covalent highlighted in that one. What is the force now for each of these compounds? Right? And unfortunately, we're going to want that thing, but I'm going to have to erase it. Sorry. Okay. What would our force be for B? Well, if it is nonpolar covalent, that results in London dispersion forces. Which force is the weakest? London dispersion. That matches my answer. London dispersion. Okay, which means a low boiling point, which means lots of gas, which means high vapor pressure. Okay. How about the other ones? In A, I had a polar covalent, which would be London dispersion. So I'm going to go in reverse order here. Now backing out the other direction. CO was polar covalent. What force would that be? Dipole-dipole. I also had a polar covalent in the OH. What force would that be? Careful, not yet. Dipole-dipole. Okay. Why would I highlight those as two different things? They're both coming out to the same force. As soon as you find you have a dipole-dipole, what should you evaluate? Do you have hydrogen bonded to oxygen, nitrogen, or fluorine? If we take a look at the first one, it was CO. Is there hydrogen there? No, so that's dipole-dipole. The other one was OH. Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine?
Yeah.
Yes, so it's not dipole-dipole, it's hydrogen bonding. Which is the stronger force? Hydrogen bonding is now the strongest force. Okay, so if I now wanted to evaluate something about melting points, I might say A is higher than B, because A has a stronger force than B does. Make sense? You should be able to go through and do that for C, D, and E as well. All of these questions are really trying to get you to identify what the force is and then rank them according to their strength. You then have to know the next step. What are you ranking them according to? Because it's a multiple choice question, if you just go through and identify what the forces are, find the one that stands out as the most different, that's probably your answer. Okay, you don't even have to read the question. You could just do that. I'm not recommending that. You should read the question. You should know what you're answering. But if you're stuck up a creek, there's your paddle. Okay, look at the forces. Make sense? You're just full of things today, aren't you?
That London field, I can't hear compared.
So we good? Make sense? Okay. So move on. Solubility, also known as miscibility. Solubility is the ability of anything to dissolve in a liquid. What anything? You mean a solid dissolving in a liquid? Yes, that's solubility. How about a gas? That's solubility. How about a liquid?
No.
That's actually also solubility. Is there a better definition for liquid dissolving in liquid? That is now miscibility. So miscibility directly refers to liquid-liquid. Solubility applies to anything in a liquid. Okay, so you may hear both of those words floating around. On top of that, you'll also hear the negative. You might hear insoluble, meaning does not dissolve. Right? Or immiscible, does not mix, okay, as liquids. So you can hear both the positives and the negatives for those. The biggest rule of thumb that you guys are responsible for is like forces dissolve like forces. You may have heard this as like dissolves like. The forces is the important part here. That's what dictates that things dissolve with each other. So what you need to go through and do is determine what those forces are for each of the compounds in your comparison. So just like we did with the last question, we would go through and say, okay, what kind of bonds are present in water? Bonds in water. Hydrogen bonding, unfortunately, is not a bond. So answer my question. What kind of bond is present in polar covalent? Polar covalent. A polar covalent bond generates what type of force? Dipole-dipole. Now that I know I have a dipole-dipole force, I can evaluate, do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Yes, which means it is best to refer to water not as dipole-dipole, but as hydrogen bonding. Okay? We've now identified the force in water. Move to the next compound. We do the exact same thing. That one becomes more difficult. Why is that one more difficult? There's more bonds. So you still have to go through and evaluate each of those bonds and decide what type of bond is present, which means what type of force. Okay? At this level, all we're looking at the very simplest, is which of those forces are similar. When you go through and take a look at that next compound, we'll jump straight to the forces. We would have London dispersion force, and then hydrogen bonding. Is hydrogen bonding similar to hydrogen bonding?
Yeah.
Those are being like, really? Yeah. It's literally the same words, which means yes. Should these two things mix? Yes. These are miscible. Right? For those of you that are old enough, you can thank me for that. After you finish this class and do pass the class, and you go out to the bar, and you can celebrate with ethanol and water, okay, which are a soluble mixture. What about the next one? H2O. What do we have? Water, yeah. Hydrogen bonding. The next compound. What's present there? Nonpolar covalent bonds, which is resulting in LDF forces. Is hydrogen bonding similar to London dispersion? No, they're literally different words. Right? And as simple as that sounds, it is way oversimplified. That's what you're expected to do at this point. Okay? So would I expect propane to mix with water? No, they have different forces. Okay? So those don't mix, those would be insoluble. Okay? Ionic compounds, we have hydrogen bonding versus ionic. Would I expect those to mix? Well, we'd say different forces, we wouldn't expect them to mix, except what do you know about sodium chloride? It dissolves readily in water. You know, when you make your pasta, you add the salt to it. Okay? Those do mix. So there's other things that contribute to solubility. Okay? When we're looking at ionic compounds, for the sake of this class, what you should evaluate for ionic compound solubility should be your solubility rules. All the way back in chapter 7. I think it's 7. Okay? So sodium chloride would be soluble in water because sodium is a group 1 metal. All group 1 metals are soluble in water. Okay? So this is supposed to get at a fancier picture of it, so let's ignore the fancier picture and just deal with the question. Okay? Apply like dissolves like rule to predict which of the following liquids is miscible with water. Okay, so adjustments that we would immediately make. Please reconnect. Like what? Forces dissolve like forces. Miscible means, okay, they mix, okay, or they dissolve. Okay, so if I want them to be miscible, this had better be like forces dissolves like forces. So these need to be like. What if it had said immiscible? Not alike. So I could write not like. Okay. That extra word can now help me go through and evaluate. So I could go through and look at each of these things. And pentanes intermolecular forces, C5H12. Well, they just gave me the formula. They didn't even give me the structure. Does it matter? You only have carbons and hydrogens, which means your only type of bond would be nonpolar covalent, which means the only type of force would be London dispersion. Next one.
Was the guy named London that created that?
I'm not sure the origin on London. The guy was van der Waals. Cyclohexane, C6H12, London dispersion. Next one, CHCl3. Ooh, chlorines. That's now polar covalent, which means dipole-dipole. Okay. The next one, ooh, a bunch of OHs, which means dipole-dipole. Last one, carbons and hydrogens, London dispersion forces. Just looking at that, that's now going to become difficult to distinguish because none of those immediately stands out. Until we add that extra layer, when you look at dipole-dipole, what should you also evaluate? Do you have a hydrogen physically bonded to oxygen, nitrogen, or fluorine? If we look at answer choice C, no. If we look at answer choice D, yes. It's not dipole-dipole, it's hydrogen bonding. So we could go through and say D is the answer, hydrogen bonding. These are talking about like dissolves like. All we've said is one of those forces. What's the other force? What am I comparing glycerin's force too. Because in solubility, it's always a mix. How do you know it's water? It's an easy statement, because you read the question, and it says mix with water. Water is H2O, which generates hydrogen bonding as a force. Is hydrogen bonding similar to hydrogen bonding? Yes. There's my answer, D. Hi. Sorry we talked a little bit too long, but I wanted to at least finish that one.